Hi guys, and welcome to Astronomy 120. Today is Thursday, October 6th. We are still continuing with the topic that we started last time. Basically, we started with the outer planets. Excuse me one second, okay? Let me do something quickly in here. Okay? Anyway, as I was saying, we're really continuing with the topic of last time, basically, where we started the idea of talking about the outer planets, systems that are past Mars, really. To be honest with you, the line, the frost line that delimits where the outer planets are and also the inner planets are is somewhere between Mars and Jupiter, and it's probably where the asteroid belt is. So that's basically where that is. So we moved on. We explored the idea of the namely the two major planets. As a matter of fact, we alluded also to the other two, namely Jupiter and Saturn, and we saw that they have those dark bands and light bands, basically, that fluctuate between one another, and we saw that those are due to the dynamics in their atmosphere, because those are mainly gas giants. As a matter of fact, we did a calculation for their densities, and we concluded just because the density of Jupiter is slightly over 1 kilogram per cubic per liter, that is, or 1 gram per cubic centimeter, or there is another unit which is 1,300 kilograms per cubic meter. It's slightly more than that of water. So that immediately basically raised the issue of the composition of that planet, that it's mainly really hydrogen and helium. And that's indeed what's going on with it, with traces of methane, ammonia, and also water in its structure. But it's mainly those two elements. Specifically, hydrogen plays a major role in its internal structure. That is not too different actually from Saturn. As a matter of fact, Saturn is kind of an odd thing in this case, because Saturn has a density that is less than 1. That's the only planet whose density is less than 1 kilogram per liter, meaning that if you put it in an ocean big enough, it would float, because the density is less than that water. So the water would really cover it. But of course, you really need to have a container big enough for it. Again, in terms of composition, is similar, with the exception of the dark band and the light bands are not that much distinct. They're not too different from one another. In other words, the distinction between these two is not as evident as it is in the case of Jupiter. If you're thinking about the other two planets, namely Neptune and Uranus, they have a bluish color because of the fact that they have high methane concentration in their atmosphere. And then the reason why you have the case for the Jupiter, and especially, and also the case of where Saturn also have that kind of a brownish color, is because of, again, the presence of those elements, especially the water in their atmosphere and how they interact with light. So that's basically in terms of composition. In terms of also another feature that is not unique to just Jupiter, namely those kind of very fast winds that generate, among other things, the red giant spot for the case of Jupiter. It's also existent, but not as much as for the other two planets, the other three planets. The others, they exist, but they don't last that long for the case of Jupiter, because it's supermassive and the winds are blowing very hard, and they blow on all of the other planets very hard. And again, it has to do with the fact that they're moving very fast around their axes compared to the Earth. The day basically on Jupiter will last slightly less than half the day here on Earth. And imagine with me for a second that it's 11 times as big and spinning super fast. So it's really spinning a lot faster than what you might think because of that huge size. So that generates tremendous amount of winds that generate those features on their atmosphere. For one another feature that is actually not unique actually to also Saturn, and that is the rings. The rings exist for all of the other planets. Basically, all of the outer planets have rings. Some of them are actually, one of them is actually easily visible with the small enough, basically, telescopes. The others, they really need more powerful stuff to see them. And we talked about the case of James Webb, the picture that was taken by the James Webb lately. for Jupiter, showing clearly the rings of Jupiter when looked at in the infrared. And the infrared basically seeing what the heat that is generated by those rings. So this is in a nutshell what we saw last time, basically in terms of composition, in terms of structure, winds, temperature. And another feature also that is extremely important for these planets is the magnetic field. Their magnetic field are many folds bigger than that of the magnetic field of the Earth, suggesting there must be some metals, basically a metallic structure inside. So the theory is basically the only element that is with huge abundance that could generate such magnetic fields is helium. I mean hydrogen. I'm sorry. Hydrogen is a metallic element, becomes metal. Helium will not work because helium, the outer shell of the helium, has 2 electrons in it and it's saturated. Okay, because the lower shell in terms of the atomic structure is the S shell, the 1s shell. And for the case of the helium, helium is saturated. As a matter of fact, helium is an inert gas. It does not interact chemically with anything. Basically, helium is helium, just like neon and argon and all of the other rare gases. Noble gases, they are called also. But hydrogen is not. Hydrogen is highly interactive because it has one shell available for it to basically either accept or get rid of an electron. So it easily interacts chemically, and all kinds of compounds, including all of the chemical organic chemistry, is based on this property of hydrogen. So what's going on in the case of these outer planets is hydrogen is under tremendous pressure, that it becomes a liquid state that we don't know how to reproduce here on Earth because of the amount of pressure required to do it. So it becomes a liquid to a point that that liquid is really metallic liquid, metal, really like iron and copper and all of the other metals that you know of. And because of its, actually it's in the same group 1 in the periodic table, if you have had a chance to look at the periodic table. So it behaves similar to all of the group 1 metals, basically, including one of them is sodium. So the point being in here is that that property of metallic property gives it the ability for it to have free electrons floating. So imagine a planet that is moving super fast around this axis with electrons basically moving. So that generates currents, electrical currents. And those currents basically by something called Ampere's law generate a magnetic field. Ampere's law relates the electric current to the magnetic field. So a magnetic field is produced just by the virtue of this motion. This is what the numerical models work, and they actually match the properties, the magnetic properties of these planets to extreme accuracy. So that must be the case, because again, we were never able to go inside these planets. I mean, the atmosphere is super thick, and they cannot really. As a matter of fact, we really don't know honestly if they have solid surfaces. But again, because of the nebula theory that we talked about way back when we were doing chapters 34 and 35, and how the solar system planets formed. Basically, that also is a good way of looking at this big planets, that they must have actually, at least according to that theory, inner cores that are rocky, similar to the Earth. But tremendous pressure that they are undergoing will probably cause them to liquefy first, and their high temperatures, high pressures, and then they even become solid, just like the core of the Earth that is solid core. So this is in terms of what we saw last time. Today, we're going to delve into another topic, really, which is kind of an extension to that topic, and that is the outer, the satellites, basically the moons specifically, okay? We're going to talk about the moons outside of the, in general, okay? And the ring systems. So these are the objectives. Again, describe the overall properties of satellite systems and define the irregular orbit. So just to give you an idea, a regular orbit is, for example, when a planet has a satellite that orbits on the ecliptic, okay, or to where the planet formed, and it orbits in the same direction, with all of the properties of what that orbit is. So basically, the orbit has to be circular, not elliptical. The closer it is from a circular, the more regular it is. So if it is any other thing, then it's an irregular orbit. which then begs to suggest that, wait a minute, then there is something that needs to be mentioned about that. Once it's irregular, where did it come from? Where this irregularity is coming from? What does it tell us about that moon and where it came from? Then compare satellite systems and their formation processes to the solar system. Again, I just mentioned basically how they're connected to, once they're irregular, we have to come up with how they came up to be. Then explain the difference between larger and smaller satellites. Again, we will see that any satellite less than 400 kilometers does not have enough 400 does not have enough force of gravity to pull itself into a spherical shape. Because if you have a large enough body, like for example the planets or the stars, you're pulling from every which way, and in this case, because of the virtue of the symmetry, the object becomes circular or spherical shape, I should say. Now, if the object, like the case, for example, we're talking about that when we're talking about planets spinning super fast, that's a spherical shape kind of smooths a little bit and has this kind of flattening effect, but still has that symmetry. But then objects that are small in terms of size, then in this case, they really don't have enough force of gravity to do that effect. And they will have like a potato shape, potato-like shape, basically, that does not have a regular shape. So that's basically the difference between them. And then describe the ring systems, their origin, and the factors that shape them. And that's where we come to understand or know about the Roche limit and what it means for a moon that it approaches so close from its host planet that basically it's going to be it's going to shred it to pieces, basically, and that's how rings basically form. So again, the Galilean system was discovered by Mr. Galileo himself, okay, and that's why they bear his name. Actually, in the early 1600s, when he took a toy and looked at the planet Jupiter, and he immediately noted for the first night 3 moons, okay. And those 3 moons, basically, they were named after basically also the same mythology that came up with Jupiter. Jupiter, by the way, it was given Jupiter, which is the king of gods, or in the mythology, is because of its dominance in the sky, as a matter of fact. And it turns out to be the biggest planet in the solar system. So again, all of the names of the others followed similar mythologies. So the first 3 moons that were discovered that first night by Galileo were Europa, which appears to be moving moves around Jupiter closer than the other 2, namely Ganymede and Callisto. Then the next night, actually, when he looked at, he saw a 4th one, and those are 4 dots basically next to the moon. So the 4th one was named Io. So these are the 4 moons of Jupiter, and they spin around the planet in about 2 days for the case of Io, to about 17 days for the case of Callisto. Io, which is the closest moon to Jupiter, is almost the same distance, or slightly more actually, than the distance from the Earth to the moon. But the Earth to the moon makes about 30 days, basically 29.5 days to go once around the Earth. Whereas Io, which has the same distance, is actually moving a lot faster around Jupiter, about 2 days. So it's a 1/30th the time it takes, or 1/15th, I should say, the time it takes for the moon to go around the Earth, for Io to go around Jupiter. In other words, for all the time the moon goes around the Earth, Io will do it in 15 times, or roughly about that number. And you ask, what happened to Kepler's law? Wasn't it that p squared and a cubed are equal and all of that thing? Yes, they are, okay? Except in this situation, the constant term that is concerning Jupiter is much, much higher than that of the Earth, because the mass of Jupiter is much, much higher. So objects, in order to orbit it, must move very, very fast. That's exactly what's going on in here. And that is the closest object. The furthest object, at least among these 4 moons, is Callisto, and Callisto is actually far away. To give you an idea about the sizes of these objects, and here is a nice picture. Let me see if I can bring this one up closer, actually, because it's important to talk about it. What is the view here? I was thinking it's. Let me move it a little bit to this side so that we see. This is actually in the book. It's actually a very good picture to look at. Again, The distance in the bottom is in kilometers, really, or yeah, the units in kilometers, but you have to be very, very, very careful with this scale. It's not a linear scale, it's a logarithmic scale, meaning from here to here, it's not a distance of it's about 10 times as big, because this is 100,000, this is 1,000,000 kilometers, this is 100,000 kilometers, this is 1,000,000 kilometers, and this one is actually 100 or 10 million kilometers, I should say. This is 10 million, this is 1,000,000. So the scale from here to here, it's a huge number. From here to here, for example, this is 100,000, this is actually 10 million. So that's what the logarithmic scale is. And you probably have seen that when they talk about the earthquakes, for example, they use logarithmic scale. So for example, between a 5 Richter scale versus 6 Richter scale, the difference is about 10 times. So that's the same thing in here. So that's something about the units in here. The Earth's moon is about 384,000 kilometers. And that's exactly what I was talking about earlier about Io. Io is slightly further from Jupiter as the moon is from the Earth. But the size of Jupiter is ridiculous compared to the size of the Earth. So as a matter of fact, the actual distance from the surface of the moon down to Io is a lot less than the distance between the surface of the Earth to the actual moon of the Earth. So that just to give you an idea, okay? So the big moons in the solar system, when we talk about them, are, first of all, Ganymede by far is the biggest moon. It's bigger than actually Mercury. And that is the third moon in terms of size from Jupiter. Then Titan is actually the moon of Saturn. And the moon of Saturn is a big moon also. It's one of the moons that actually have a lot of promises in terms of its first of all, its atmospheric pressure is about slightly higher than that of the Earth. So technically you could stand on its surface without feeling any kind of problems with the pressure. The temperature is very, very low though, so you cannot really survive the temperature unless you have protective suits. The atmosphere is actually not that bad in terms of its atmosphere. It's mainly nitrogen, which is exactly what the atmosphere of the Earth is, which is mainly nitrogen. The atmosphere of the Earth has oxygen, and it's about 20% of it is oxygen. Titan does not. But Titan has on its surface a lot of water also in frozen solid ice, which technically you could melt and also make out of it oxygen to breathe and make also out of it water to drink. So Titan has a lot of promises, and this is one of the places that usually in sci-fi movies and things like that, this is one of the interesting things. And actually scientists are also interested with it because of the fact that if potentially we could land anywhere with mankind, we could do it on Saturn. The only trouble with Saturn moon, Titan, the only trouble with this moon is very, very, very far. I mean, just to go to Mars right now, it takes you about 6 months. But for Jupiter and Mars is nothing compared to Saturn. But to go to Saturn is very far away. So that's really part of the challenges that we have. But we had actually a project, we had a lander on it, and we took pictures from the surface. So we have a good idea, at least compared to the other object and how it looks like. So it's the second moon in the solar system in terms of size, and it's actually bigger also than Mercury. Callisto, which is the furthest of the big moons of Jupiter, from Jupiter compared to the biggest, the third furthest, or the fourth furthest in terms of the distance, in terms of big moons of Jupiter, it's actually the third moon in the solar system. And it's slightly less than Mercury in terms of size. So these three moons are actually either comparable for the case of Callisto or bigger than Mercury, than a whole planet. Just to give you an idea. The fourth moon in terms of moons in the solar system is actually Io. Io is the closest moon in terms of size, the big moons that is, to Jupiter. And this is actually a very important moon that I need you guys, for those sitting in Astronomy 125. I think it's the next lab, not today's lab. We will be doing, we'll be measuring the mass of Jupiter using this moon, basically, and how fast it goes around Jupiter. So again, Jupiter, Io is the fourth moon in the solar system. It's smaller than, of course, Mercury. But it's also an interesting object on its own because its surface is a really, really, really highly volcanic surface. Why, you're asking? Because its proximity from Jupiter. So Jupiter is pulling on it on one side, And the other three moons actually are pulling it from on the other side. So they are pulling one from the other and the other three from the other. If you're wondering what's going on with Europa, the same thing also, Europa is under the same tidal forces, except Europa is being pulled upon by three, two from one side and two from the other side. If they're lined up in such a way that this is the lineup, but some other times, Io will be on the other side of Jupiter and everybody, including Jupiter, is pulling on it on one side. Because of this, this is called tidal forces. It's like you take a dough, for example, trying to prepare your pizza, and you start kneading it, okay, working it. It gets hot inside. So that's basically what's going on with it, and it erupts in volcanoes. So this is the fourth moon in the solar system in terms of size. The fifth moon in terms of size in the solar system is actually Earth's moon. So Earth's moon is an odd moon, as we said before. It's in the wrong place. It's big for its where it is, and it's the fifth largest moon in the solar system. So it's an exception to everything else. And we discussed the Earth's moon in detail in one of the previous units. Then the sixth moon in terms of size is Europa. Europa is actually the second moon in terms of distance from Jupiter, in terms of the large moons of Jupiter. Jupiter has about 70 moons altogether. Okay, and it's almost every once in a while we discover new moons for it. So it has a lot of moons. All of these dots that you see in here, they're actually moons, including Amalthea that we saw last time in the picture from James Webb. So these are the moons of Jupiter in terms of size. Europa is the sixth largest moon in the solar system. Then comes Triton. Triton is the moon of Neptune, okay? Note the color coding in here. These colors, all of the yellow moons are actually regular moons. All of the red moons in here are actually odd moons, okay, including Triton. So Triton and the other odd moons, they orbit either in the wrong direction, everybody is spinning in one way and they orbit in the other direction, or they orbit completely in a different orbit than where they're supposed to be, or they have an eccentricity that is much greater than one. So basically they are eccentric. And the only explanation for that is that these moons are captured moons. So that's basically how we're going to describe them. As a matter of fact, starting probably from Triton, we're talking about small or average moons. For the case of Uranus, Miranda, Ariel, Titania, Oberon, and Embriel, they're all actually small moons. And also the vast majority, or all the other moons of Saturn, with the exception of Titan, they're also Dione and Enceladus. Enceladus actually is a very, very interesting moon also that has so many features that we're going to be talking about them. And then Europa also. Europa is actually an interesting moon also for Jupiter because of the fact that it has a lot of water in its ocean, in its underneath of its crust, and that ocean is a big one, suggesting that probably because it's a salty ocean, and you're wondering, how do we know if it's a salty ocean or not? Well, it seems like when we did probes on it, it seems like the particles that were coming off of it, they respond to the magnetic field, therefore they must be charged particles, therefore it must have salt in it. So it's based on the magnetic properties that they determined it's salty, just like the oceans here on Earth. And suggesting that there is life probably, so potentially it has life as we know it, carbon-based life as we know it in its ocean. So it could be a very, very rich moon in terms of life forms. And of course, Io is impossible to have life, at least as we know it on its surface, because of the volcanic activity on its surface. So in terms of moons of Jupiter, again, the big moons in general. So let me go back into the normal size in here. Go back to 100%. That's good enough. Okay. So again, these are the moons of Jupiter. I mentioned them earlier. Look at the shape or the form of Io. Io has this yellowish color because of the sulfuric acid, sulfur basically that is coming, basically spewing from its surface, and it has all kinds of eruptions on its surface. And when the probes went by it and took pictures, they saw all kinds of activity because the next pictures they took were completely different, suggesting that its surface is highly changing because of those volcanic activities. The surface of Europa is kind of smooth in general, suggesting that it has an icy structure. It has a higher reflection coefficient, meaning that it's made out of water, but it has all of these ruptures, these lines in its surface, basically these cracks, suggesting also that its surface is undergoing heating underneath, and those result from time to time in water basically coming out of the surface in sort of geysers, basically coming from underneath the surface to the crust. So again, that's how we know it has a lot of water on its surface, and that is the next moon closer to it. In terms of structure, or in terms of surface, at least for Ganymede and Callisto, they have this highly cratered form similar to basically the moon and Mercury, suggesting that their surface is a lot older. In a sense, they did not have a lot of weathering. They did not have a lot of how should I put it, volcanoes or kind of tectonics whatsoever. So they are actually very ancient, almost as ancient as the moon is. Titan, on the other hand, looks similar to Venus. If you guys look at it from outside, Venus does not show any features because of its super thick atmosphere. Same thing is going on with Titan in here. Titan has also a thick enough atmosphere that basically gives it this color, and that's the form for it. Again, this is basically in terms of big moons. In terms of also the moon of Triton, the moon of Neptune, it looks awfully similar to the dwarf planet Pluto, actually, because it appears to be of the same caliber, and apparently it was actually a dwarf planet in its past, and it was captured by Neptune. So Neptune basically, Triton wandered too close from it that it captured, became one of its moons. That's why it has all of this irregular paths and so on and so forth. Now, I mentioned earlier the 400-kilometer limit, that in a sense that if a moon is bigger than 400 kilometers, it's going to have this spherical shape. And if it's less than 400 kilometers, just like Amalthea also and all of the other, they don't have this spherical shape. So basically they become kind of a regular shape, okay, just like potato-like shape. Now, these are the medium-sized moons. These are basically in terms of mainly the moons of Uranus, all of them actually, including Titania, and they have also a different kind of reflectivity because it depends on their surface and what's on its surface, suggesting that probably some of the dust that formed from before, including ash itself, that either was from another moon that basically collided with them in the past, or actually from asteroids that hit them or something like that in the past. So that's basically, and sometimes they're bright surfaces in this case from whatever inside came out. So these are the different moons that we have. They're the medium-sized moons, including Mimas, Enceladus, Dione, and Rhea for Hyperon. Hyperon actually a little bit irregular. Iapetus for Saturn. So those are the moons that we have in here in terms of Amalthea. I was talking about it, and this is what we saw last time from the James Webb. It does not have that 400-kilometer limit, so it's not a spherical shape. So these are the general properties of these moons, okay? So this is the Iapetus. Again, one half is white, the other one is very black. It is tidally locked with Saturn. So the same phase, and that's another point that I didn't mention when we were talking about earlier about the 4 moons of Jupiter. The 4 moons of Jupiter, they're actually tidally locked, although they're kind of just like the moon of the Earth, meaning that they show only one face to the if you can stand on Jupiter and look at those moons, you will only see one face of that moon all the time facing the planet. Now, there is also another phenomenon, and that's actually why I came back to this one, is because of there is something called resonance, and the resonance is really what causes those tidal heating. Because for each rotation of the moon, for example, Io, you have 2 rotations for Europa and so on and so forth. So these ratios are either 1-to-1 for the case of the moon and the planet, but for the case of the moon and the, I should say, no. Yeah. And for the case of these planets and also themselves, they have those ratios. So at some point, they will all be lined up in the same direction on the same side, and some other times they will not, because these ratios are whole integer numbers. So, and that is what causes tidal heating. And you're asking, how come? Is this a coincidence? Did they align themselves by accident so that the ratios are this way? No, actually, over time, the moons move in and out. So just because of the tremendous forces of gravity from one side and the other, until they fall in that resonance. Once they fall in that resonance, then they basically are they're stuck in that position. So it's really an adjustment at the end. For the case of the Earth and the Moon, of course, the Earth and the Moon were very close in the beginning, and then it's receding. As it recedes, it slows down, and so does the Earth. Okay, so the day gets longer on the Earth. So this is an interesting property of this moons in here that we have to understand in terms of tidal locking. Okay. Again, we talked about soot in this case, and that it is probably residue from another moon's destruction. And this is actually typical for all of them. And as a matter of fact, you see this irregular shape in here that seems to have fallen. So here is what's going on with the apparatus, because that's really suggests something interesting. If you look at the moon itself, right on the equator of the moon, it's a little bit, it's like you stitched it, and you stitched it was protruding, it's coming out. So what's going on in this case is, so whatever collided with it in the past, it went in a ring around it, and that ring starts to fall on the moon. And when you go in a ring, you don't go on the top, you don't go on the bottom, you go on the axis of symmetry. That is the place where there is actually the maximum gravity in this case, because if you go to the top, you're being pulled more toward the bottom until you settle in that position of symmetry. And then as the matter starts to fall, it's going to fall on the axis of symmetry, in which case, in this case, it's this region in here on this, and this in the moon. Okay, so again, we have a lot of theories, and they all seem to fit exactly with our observations. So everything looks beautiful in terms of our explanations for this thing. Sometimes we don't know how they look like, so we'll try to come up with better explanations until we come up with a right model. This is how science works, guys. Okay, Enceladus is the other interesting moon in here. It has these geysers that you see them ejecting from the moon. And so again, all of this is coming from what is known as tidal heating from inside, when you have a moon that is tidally locked with its host planet or with the other moons, and then they start pulling it on one way or the other. So that generates heat inside. That heat will melt the water inside and actually keep it to melt, and then its temperature rises enough so that it erupts, just like volcanoes here on Earth, except that they are at lower temperatures, much lower temperature than the volcanoes on Earth, because the volcanoes on Earth are actually from magma that is coming at tremendous temperature compared to the Earth temperature. Same thing in here, compared to the surface temperature, is this liquid water at 0 degrees Celsius is tremendous temperature. When you're talking at 130 Kelvin, 273 is a huge temperature. Okay, so that's basically what this is, what's going on in here. Again, this is Miranda. Miranda also has this large faults on it, okay, that they basically dwarf any kind of mountain, or actually the Grand Canyon on Earth in here. Grand Canyon, if you happen to go to it, only about what, a mile or two down. This one is 20 kilometers or 12 miles, basically, the cliffs are. So again, suggesting about a violent past, okay, that from either tectonics or different kind of collisions and things like that with this moons. So again, in terms of ring systems, as I was saying earlier in the beginning, when Mr. Galileo looked at them, that he was puzzled with them. He didn't know what they were. He went back years to the planet Saturn when he looked at them. It took later on some work by Cassini and also Huygens, and then later on by Mr. Maxwell, who recognized that they cannot only be basically made out of tiny particles that obey each and every one of them Newton's laws of gravity and also Kepler's laws, and they also obey it. So again, you have different rings that are named A, B, C, and the separation between A and B is what is known as the Cassini division. So again, all of these things are part of the property. So if you happen to look at it, now we know actually that there are more rings actually, that they seem to be, the structure is far richer than what we can think of. Again, the rings are super thin, compared to the size of Jupiter. So they are extremely, extremely thin. If you were to look at the planet right at the right angle, when the rings are at 90 degrees, you wouldn't see them. So the rings disappear completely from view because you're looking at that right angle, because they are super thin, okay? Much, much thinner than what you might think, even the proportions of the Earth, but because the planet is huge, that's why you can see their shape in here, okay? Again, when you look at them up close, you will discover that this gap seems to be actually driven by something which is kind of strange. Actually, the gaps themselves, they have also rings in them, and they have sometimes moons that seem to be basically positioning themselves either above or below, or in front or ahead of these rings. So suggesting that those moons are actually the ones that seem to be shaping these rings and this also gaps. And those are the so-called shepherd moons. Okay, they have a lot of them. Saturn has a lot of them. Okay, the ring structure is not unique to Saturn, but it's also for all the moons. Okay, when we looked at Uranus when it was passing in front of a distant star, or was it Neptune? One of them anyway, it doesn't matter which. The point being in here is we discovered that the rings exist for the others, and then we started studying them extensively, and we saw that the ring structure exists for all of the other planets, okay? So again, I mentioned the shepherd moons in here and how they regulate and they organize these rings and how they put them together and create those divisions, okay? So those are tiny moons, not big moons, the one we were talking about. They don't even have regular shapes. Here is what's going on in here. If you model, and I think I have software, I probably will model it for you guys. If you come within 2.44 planetary radii, and I know we have a lab, so you have to be careful with this number in here. So if the moon is within this limit, okay, it starts to break down into tinier and tinier particles, forming either some of them will fall straight through, and it starts, of course, to orbit around the planet, and that is what is known as the Roche limit. Again, this is basically how the rings basically also form. So this is the origin of their planetary rings and how they form. So all of these outer planets, they have a lot of moons. Some of them are actually broke not too long ago for the case of Saturn, and they have the ring structure that we see today. Others, for the case of the other planets, broke a long time ago, and then now we have remnants of those. And is this process over? No, there's probably more moons that could go through the same process, and this process could repeat. As a matter of fact, at some point in the past history of the Earth, also Earth looked like, to some extent, one of these planets because of the fact that the moon collided with it and actually created that debris. So again, this is the unit for this week, okay? We still have actually 2 topics. Let me check quickly something in here. Okay, I have homework 4 with you guys. And homework 4 has, this is what I'm going to do with it, because it has a lot of problems in here and I really don't want you to spend a lot. Let me check with you. Let me share with you the screen first. Share. So this is what I'm going to do. I'm going to record the whole session just for this one alone, for this homework. And I'm going to attach it to the same place where we do recording. So right now we have last Tuesday recording in that section, and we will have this today also. But I'm going to add another section, hopefully no more than 20 minutes, just talking about these problems and how to do them. So again, these problems are: Venus's atmosphere contains this much kilogram of carbon dioxide, CO2. If all of the oxygen atoms in the carbon CO2 were combined with hydrogen to form water. So basically, here is how the problem. You know how much carbon dioxide you have, which is CO2. What you want to do is remove the oxygen out of it. The oxygen represents, because the carbon has an atomic mass, and you need to know the atomic masses actually to do this problem. Carbon has an atomic mass of 12. Oxygen has an atomic mass of 16. but you have 2 oxygen in there. So it's 32 actually, because 16 grams per mole and 16 grams per mole will give you 32 grams per mole for carbon dioxide. Obviously, you have this many atoms. So you have 2 of them plus 12 from carbon. Carbon, remember, its atomic mass is 12. That's 48. So 32 out of 48 of this much carbon dioxide is actually oxygen. Because again, 32 out of 48 for each molecule of carbon dioxide is oxygen. So now you can find how much oxygen you have in here just by doing 32 divided by 48 times this number. That tells you how much oxygen you have. Now you need some hydrogen, and you need the hydrogen to form water. Now, looking at the atomic mass again of this 2, the atomic mass of hydrogen is just 1, and the atomic mass of oxygen is still 16. But you have 2 hydrogen atoms in here. 2 times 1 is 2, plus 16, that's 18. That means the mass that I find in here in terms of oxygen, I have to multiply it by 18 over 16 to find how much water I'm going to make out of it. So now I have the mass of water. Again, I'm just giving you an idea. I'm going to go through the numbers again in the recording. Hopefully I'll post it this weekend for you guys so that you can do this problem and understand it. And again, it's given to you in here, the atomic masses. So now you know how much hydrogen, water, H2O, basically you have in terms of mass. So the question is, compare this mass to the masses of the Earth's oceans. The Earth's oceans have 1.4 times 10 to the power 21 kilogram. So from here, you have a mass of water on the surface of Venus that you can take all of the carbon dioxide of Venus and make it into water. Basically, planet becomes habitable because of the fact that it doesn't have much carbon dioxide in the atmosphere and has plenty of water now. But then you compare the 2 amounts by doing a ratio of one of the other, and you see that the ratio still favors Earth. Okay, even if you take all of the atmosphere of the Venus, take all of the carbon dioxide in its atmosphere and convert it to water, still Earth will have more water. Just go ahead and do this problem. Then from the previous problem, how deep an ocean would this water produce if it were the same depth everywhere on the surface? Okay. The density of water, it tells you in here, it's 1,000 kilogram per of water fills a cubic meter. So 1,000 kilogram per cubic meter, or 1,000 or 1 kilogram per liter. It's the same thing. So basically, what I want to know is whatever number I find in here in terms of mass of the water, it's going to be in kilogram. I have to divide it in 1,000. Then I know the cubic meter, because that's the density of water. 1,000 kilograms of water is 1 cubic meter. But whatever number I end up with from here, from the previous problem, the mass of water on the surface of Venus that I make up out of it, basically now I know how much volume. But I can use a formula, and it's not given to you in here, so you really need to know to use that formula, would give me the surface area of Venus. Surface area of Venus is a sphere, and the surface area is 4 pi, which is just a number, times the square of the radius. And the square of the radius is just roughly, it's almost the same square radius of the Earth. So now you have the surface area. You want to know how deep that water needs to be. You have the entire volume, you divide it by the surface area, and you're going to find the depth of the oceans on Venus, provided that the water is uniformly distributed throughout the entire planet. This is not a far-fetched assumption, by the way, because the surface of Venus, if you guys remember from units way back, units 41, is that it's super, I mean, it's almost the same distribution. It has very, very high points and very low land. So it's going to be a good assumption. You will notice that the oceans on Venus will not hardly have any kind of less than a kilometer in depth, whereas the Earth in here can go as much as 11 kilometers deep. So again, this reiterates the first problem that Venus, even it's in the best case scenario where you take all of the carbon dioxide and convert it to water, still doesn't have enough water compared to the Earth. Now, it doesn't mean that you solve the problem, because you don't know how to take all of the carbon dioxide and make it into water. But if somehow you do, this is what you end up with, okay? And then problem 13, Kepler's third law describes planetary orbital sizes to relative to Earth, which is assigned a size of 1. And one method for finding absolute orbital sizes is to use radar ranging between planets. Use Venus's scale orbit, which is 0.2723, And the observation that a radar signal takes 276 seconds to make a round trip from the Earth to Venus when they're minimally separated to find how many kilometers are in astronomical units. Again, this is, you need to know the speed of light is 300,000 kilometers per second. And this is basically how long it takes for it to go back and forth between the Earth and Venus. But then this is how far Venus is from the Earth, from the sun, I'm sorry, okay? Then take the time it takes for the light to go back and forth and multiply it by 300,000 kilometers, because it covers that many per second, but you have 276 seconds. And now you have already the distance actually in back and forth, the distance for light to go back and come back, basically, between the Earth and Venus. You divide that by 2, now you have the distance between the Earth and Venus. Subtract that, convert that first of all to an astronomical unit, and now, because the astronomical unit should be 150 million kilometers, so you subtract that 1 from 0.723, so it's going to be 0.28 something, or 0.2 something, okay? So just 1 minus this number, so it's going to be 0.7, 7 in here, 7, and 2, 0.277, okay? 0.277 astronomical units takes this many times, and you'll find the kilometers exactly, okay? Then you just divide by that number, and you'll find how much an astronomical unit is actually in kilometers, okay? For this one, it's better not to use 300,000 kilometers for the speed of light. It's better to use a more accurate value, which is 299,792, I think, or something like that, 794, I think, like that, kilometers per second, okay? That will give you much more precise value. And this problem, Venus and Earth make their closest approach to each other, inferior conjunction, every 583.9 Earth days. Use a diagram, and it gives you the figure on the page, okay, from the book, or math to show that nearly the same side of Venus faces Earth at each closest approach. So if you do that, and you know the cycle of how long the Venus will rotate around its own axis, which is the day on Venus, provided it's going backward, and also how long it goes to go around the moon, around the sun, I'm sorry, you're going to find the ratio to be an exact number, which is about 5. And that will give you the same phase as it does. Otherwise, you can draw it, okay? Earth covers about 1 degree per day in its orbit, because it goes 365 days, and 365 days goes around the Earth once. And the circle is 360. That's why it's roughly 1 degree per day. Okay, that's how it's covers slightly less than 1 degree, but it's still roughly 1 degree per day. And the solar day is slightly longer than the sidereal day. Remember, the solar day is 24 hours, whereas the sidereal day is 23 hours and 56 minutes, okay? If Earth spun in a retrograde direction like Venus, but it still had the same sidereal period of 23.56, how long would the solar day be? Well, in this case, it's just going, instead of going to be less, it's going to be, I'm sorry, instead of going more than the sidereal day, it's going to be less than sidereal day. So in other words, the day on Earth will be 23 hours and 49 minutes. That's giving you basically the bulk of these problems. But again, I'm going to have a full detailed video. Hopefully, I'll try to work on it tomorrow. Tomorrow I have a department meetings, but after the meeting, I'll try to get it to tomorrow. If not, worst case scenario, I'm hoping by Saturday, you will have the video up and running so that you can do your homework. If you don't see it, I would hope that one of you guys will send me a reminder that you didn't see the upload for the homework to get it going. Sounds good? Okay, very good, very good. Thank you, guys. So I'm going to stop the recording right now, and I will see you guys on Tuesday. What day is that? October 11th. Okay, same time. For those of you in the lab, I will see you later on today. Thank you, guys. Bye.